So data gathered on the shopping patterns during the months of April and May of high school students from Serenity High revealed the following. 38% purchased a new book bag. So this is going to be event A. 15% purchased a new pair of tennis shoes. That's event B. And 6% purchased a book bag and a pair of tennis shoes. So when we do independent events, first of all, what would this actually mean in like real world terms? That means that the likelihood of buying a book bag does not influence buying shoes. Okay, that's what it would mean in like real world terms. Now let's actually see if that is a true statement. So when we find independence, what is the formula for that? Okay, cool. So we're going to take 0.38 and we're going to multiply it times 0.15. Okay, so again, we're multiplying event A times event B times event B. And that's going to give us 0.06 roughly, 0.057, which is equal to this guy, right? Which is at 6%, right? So are these two events independent? Yes. Okay, and I just proved that algebraically up here. I'm not gonna write it down there. Take a second. Today we're gonna be finding the probability with independent and dependent events. Again, we've already kind of gone over this stuff, so this is just kind of like a recap of what we've done. Okay, so independent events are two events from the same experiment for which the probability of one event is not affected by the other event occurring or not. Okay. So for instance, an experiment consists of spinning each spinner. Find the probability of 2 and C. Dependent events are two events from the same experiment, which probability of one event depends on the other. Okay, ready? A sock drawer containing 10 black socks and 6 blue socks. What's the probability of getting a pair of black socks? That means that the first pick is going to affect the next pick. That makes sense? Okay, there's always a question on the final that's like, you got a bunch of marbles in the bag and the marble was picked out and then replaced. Are these independent events? Okay, let's think about that really quick. You pick out a marble and then you replace the marble and then you pick another marble out. Are those independent events? Yes, they are. If I take out a marble and I don't replace it, then that's dependent. Does that make sense? If I replace it, they're independent. If I don't replace it, they're dependent. Make sense? No. Same marble. I put it back in the marble. Okay, so go ahead and look at example. Okay, all right. So, yes, ma'am.
Okay, I'm debating whether or not.
Okay, so let's take a look at it. Yeah. Okay, so what's the probability of rolling a 6? 1 out of 6. Fantastic. What's the probability of rolling a 5? Okay, so what's 1 out of 6 times 1 out of 6? So first of all, 1 out of 6 is point. That's 0.1. 0.116. So if I took 0.116 and I multiplied it times 0.116, that's going to give me about 2.7 or 2.8%, depending on how you want to look at it.
What I meant to say, but I answering the wrong questions.
Yeah, 0.1. Yeah, sorry, y'all. Listen. Okay, now fraction versus decimals. Really quick. If I multiplied 1 out of 6 times 1 out of 6, This is actually going to give me 1 out of 36, which is 2.7, 2.8%. Okay. Okay.
We were wrong.
Go ahead and take a look at this one. Oh, going back to here. We understand that these are independent events. Okay, the likelihood of like that happening is very, very small, but they're independent events. Go ahead and take a look at this next one. Yes. Okay, we got these marbles. You're trying to draw 2, okay, and they're not replaced. Okay, you have to pay attention to this fact that it's not replaced. Okay, so we want to have blue marbles. How many blue marbles do we have in total? Okay, out of how many total? Okay, and we also want to draw them again. We're not replacing it, so how many marbles will we have left? So we had 9 originally. We took 1 out. So we're gonna have 8 and 3 in the top because we potentially would have taken out a blue marble already. That makes sense? So when we multiply these fractions, I'm going to do it the fraction way and then I'll do it the decimal way in just a second. 4 times 3 is going to give us 12. 9 times 8 is going to give us 72. Now, yes, you could reduce that fraction. Okay, and if you do that, you're going to get 1/6. That's forever. And 1/6 is also the same thing as 17% or 16.7, depending on how you want to round. Yeah. So you would take a marble out. That means that you have 8 left. And we're hoping that it would be a blue marble. So the first one, the probability would be 4 out of 9. The next one would be 3 out of 8.
Oh, like, okay.
Yep.
Take 1 out, we got another one.
Okay. Now these are dependent events. Okay, because one impacts the next one.
Because there's a lesser chance you'll get blue.
Right. Okay, example 3.
Name.
Okay, how many of people's parents play the lottery? Do you know? Okay. Secretly, they play the lottery. No, I'm just kidding. Oh, that'd be awkward. Okay, so do you know how many tickets you would have to buy in order to win the lottery? Okay, you would have to buy a lot. There was actually like a Harvard research team that went out and bought they did like a group of people went out and bought like all these tickets and stuff. And apparently it's like you have to win or you have to buy 64 tickets in order to break even. And then you would have to buy like 200 in order to like strategically win. Okay. So like think about it though, there's like a $10 one and then there's like a $1 one. So you're still spending like a chunk of change. I mean, like that's expensive.
I mean, to win like once more.
I mean,
like it'd be worth it.
Yeah.
If you feel like you have a high chance of winning, I feel like it's worth it.
All right. So, and one thing that y'all know, like all those like different, like The Price is Right, Family Feud, that kind of stuff. Like they win a lot of money, right? You know what the government does? They take half of it. So if they win like $40,000, they only get $20,000 of it. Oh, and when they get a free car, they have to pay taxes on it. So you have to like pay 30% of what the price of the car is back to the government. I'm serious. It sucks. Okay. I'll go on those shows. Okay. So how many tickets in total do I have? Okay, good, because I was not doing that math. All right, so if Christo gets the first poll, that would be 5 out of 23, right? Okay, on the next one, how many would he have? 4 out of 22. So 5 times 4 would give me 20. And then 23 times 22. You said 526?
Oh, that's about Crystal. There's with everything.
Okay, so then we would take 20 divided by 506. And that would give us not 40%, 4%, right? Okay, so you got a 4% chance of pulling 2 tickets from Christo. Now there's only 22 tickets. That's like a small scale lottery, right? So on the first one, it says a person chooses a crayon at random out of the bag, uses it for a bit, puts it back in the bag. Second person comes to get a crayon, chooses at random out of the bag. What's the probability the second person gets a yellow crayon? So that's okay. So how many crayons do we have in total? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, cool. It doesn't even matter about the first person, unfortunately. Like the first person did not matter in this story. So that's going to be 1 out of 8, or for those of you who did a percentage, that's going to be, that's okay, 12.5. I saw a lot of those. A lot of people said 13%. That's okay. I would have taken that too. A person chooses, I'm reading, choose at random out of the bag, walks off to use it. A second person comes to get a crayon, chooses at random out of the bag. What's the probability that the second person gets the yellow crayon? Okay, so that would be how many yellow crayons would we have? 1. And hopefully they didn't take the yellow crayon, right? Okay, so that's gonna be 1 out of 7, which is gonna be how many? Okay, I would have taken 14%. Okay, so most of y'all got those. Most. So that's good. All right, last little thing. Put this on your notes. Okay, tell me what you got. I didn't do it. First one. 1/10. 1/10? Or 10%? Wow. Okay, what about the next one? Okay, what about the next one? I agree because if you put it back, her result isn't affected. Okay, because it was replaced. Okay, and they're also equal, right? They have the same. All right, cool. Good talk.